Let's talk about the four surface area formulas. So what you see on the screen here is the four versions of this formula that represents the area of a surface of revolution. So there's two different features that can vary here, which is how we get four different formulas. So you could have y equals a function of x or x equals a function of y. And you could be rotating that bit of graph about the x-axis or the y-axis. And among each of these, there are slight variations in the formula, specifically right here and right here in all of them. So 2 pi something, 1 plus something underneath here. All right, so let's talk about how you can figure out what goes where in your particular situation. And then we'll end with an example done two different ways. Okay, so first let's think about if you're given y equals a function of x. Sometimes it's explicitly given this way where the problem will say like f of x equals a formula. Sometimes though, it's just x's and y's mixed up. And really what this requirement is, aside from having just solved for y, which you might have to do, is that it's literally a function. So this has to like pass the vertical line test. So you can have a shape like a parabola. This will pass the vertical line test. This one you would have to do this way. If x equals a function of y, this would have to pass a horizontal line test. So this you would have to use if your graph were like a sideways parabola, because then it can't be written as y equals a function of x. You would have to go the other way. So sometimes you have the option for solving for x or y, but you just want to be extra certain that it's actually a function in the direction you're saying it is. Okay, so let's say you have y equals a function of x, and you're rotating either the x-axis or the y-axis. We won't worry about that yet. So in this category, both of these integrals have an f prime of x in the portion of the formula that echoes the arc length formula, right? So under the square root, 1 plus derivative squared. If you start with an f of x, f prime of x goes in that spot. And if you start with g of y, g prime of y goes in that spot. So whichever way you decide to put your formula, you're going to differentiate that formula. And that'll tell you not just what goes in that spot, but what variable you're integrating with respect to. So if you have a derivative in terms of x right here, that tells you this is an integral with respect to x. So you'll have bounds of integration a and b. These are the x values that create the shape. Same thing down here. A and b represent x values because you're integrating with respect to x. Whereas on the other side here, when we have x equals a function of y, you have a y formula as your derivative. So you're integrating with respect to y. And then the bounds of integration are y values. We use c and d just to call attention to the fact that they wouldn't be the same numbers as these over here. So these would also be y values. Okay, so whichever way you have it, you're going to do your derivative first. That informs this whole part of the integrand, the d whatever at the end, and the bounds. So then the only thing left to decide is the part that goes after the 2 pi. All four of these are different, and that is determined by the rotation. Okay, so now let's switch to thinking about this in rows. If we're rotating about the x-axis, let's get a little sneak peek of what that would look like, right? So let's say we just have some little bit of graph, and we're rotating about the x-axis. Like that. So the radius of one of the circle kind of cross sections here, the radius is a vertical distance here. So that would be the y value of this point that's on the curve. So if I can say y, I'll just say y, which is what this one does because it's in terms of y. But in this one, we can't, like we're in terms of x, so we can't just put a y in that spot. So we put f of x instead because they're interchangeable. Y and f of x are the same, and they're both giving us this vertical distance. If we rotate about the y-axis instead, it's a little graph chunk here, and we rotate it this way. Now the radius of one of those circular cross sections is a horizontal distance. So if I can say the x value at this point, I can just say x, right? So in the integral that's in terms of x, you can just put an x for the radius. Whereas over here, this was in terms of y. So instead of x, we put the g of y that it's equal to. And once you have that spot filled in, your whole integrand is ready to go. All right, let's actually see this in an example. I'm going to do this example two different ways to kind of make a point about the formula, because y equals x cubed is a function in either direction, right? So if I back solve this for x, it's still a function of x in terms of y, so it'll work both ways. Okay, so as it's given, we have y equals x cubed. This will be our f of x equals x cubed. And we're taking the point 1, 1 to 2, 8. So that's just two different points on this curve, and rotating about the y-axis. Okay, so I want to represent the surface area of the solid being described. In the arc length portion, I'm going to put 1 plus a derivative formula squared. Now, if my formula is x cubed, I'm going to put 3x squared in this spot. That's my f prime. And that tells me what variable I'm in, right? So now I know, okay, this whole integral should be in terms of x, so I can put dx here. And then the bounds of integration, a and b, will be the 1 and the 2 of these points. Now the only thing left to fill in is 2 pi radius at the beginning. So 2 pi, and then we have the spot for the radius. Now it matters how I'm rotating. So if we're rotating about the y-axis, we have this little bit of curve, and we're rotating this way about the y-axis. So the radius is going to be a horizontal distance. So if we're in x, I can say x, which is what we have. And if we were in y, we would say g of y instead. So this is the integral I would need to compute for the surface area of this thing right here. All right, so now let's switch our perspective and answer the same question. So now let's say y equals x cubed. We're going to turn that into x equals the cube root of y. It passes both the horizontal and vertical line test, so we can interpret this any which way we want. So this is going to be my g of y, cube root of y, which is y to the 1/3 power. Okay, so now when I do my surface area formula, I have 1 plus derivative squared. And now my formula is y to the 1/3, so its derivative is 1/3 y to the negative 2/3. And that tells me this integral will be in terms of y. So I put a dy, and I grab the two y values of these points 1 and 8 as my bounds. And now finally, we want to put 2 pi radius in the front. And I already have the image going here. The radius of one of these cross sections is a horizontal distance, which is the x value of this point. The problem is we can't say x anymore because this integral is in terms of y. So we want the y equivalent, right? So we take the expression of y instead, and we'll put that cube root of y right there, or y to the 1/3 is fine. So if you can find a way to actually compute these all out, these should turn out to be the exact same number, but I will leave that up to you to finish it off.